Thanks everybody for joining us. My name is Jeff Sellers. I'm the 3D printing salesperson for TPM, handling North Carolina, Virginia, Tennessee, and that general mid-Atlantic area. Another rep who's on the phone right now, Scott Kvostis, works out of our Columbia office, and Scott handles South Carolina, Georgia, Alabama, and more the southeast area. We also have Lishan Mu. He's an application engineer at Markforged. He's going to be doing the balance of this presentation, which is titled From CAD to 3D Printing with Markforged. We're going to kind of take you through some CAD designs and how you manipulate them and get them over to a Markforged Eiger software, and then get your 3D printing output with your parts. One of the things we wanted to point out during the presentation, and you can type in questions, Chris Ivan, our TPM application engineer, is monitoring this. If they are TPM related questions, he might respond immediately. If they're more Markforged related questions, we will table those till the end of the presentation and have Lishan field those, after he's done with his presentation. I just wanted to give you a quick overview. I'm not going to spend a lot of time here, but there is a wealth of information about TPM out at tpm.com, our website. We also have a LinkedIn channel that we post information to almost on a daily basis. But if you are unfamiliar with TPM, on the far right side, you can see the various software and hardware solutions that we represent for our company. And we are a 45-year-old company. We're family owned. We provide hardware, software, services, training for manufacturing, construction, architectural, product development, design, engineering related companies. And we've been doing that for the past 45 years. So at this point, I'm going to be quiet and turn it over to Lishan. So Lishan, go ahead and run with it, and I'm going to mute my phone for the time being.
Okay, thank you, Jeff. I appreciate it. So once again, guys, thank you very much for your time today. My name is Lishan Mu. As Jeff introduced, I am an application engineer at Markforged. I cover the Southeast and South region, so everywhere from Virginia down to Texas is the region I cover. My role is to help our customers identify areas in their business where they can leverage Markforged's additive manufacturing technology for their business needs, find a quick return on their investments, and transition from the old ways of doing things to the new ways of doing things. So a little bit about Markforged. We do both metal and composite printing. Our metal printing, we're actually the #1 metal 3D printing company in the world. We've shipped over 200 full systems to over 20 different countries, and we're ramping up to sell and ship 750 units a year. And that's with our expansion into a new manufacturing plant up in Boston. We've now expanded to 2 separate offices. And we were named by Deloitte as one of the top 10 fastest growing technology companies in North America. So the agenda for today's webinar, we're going to talk about why use 3D printing. And it's probably the reason you guys are all here today is understanding I'm doing something one way today, why should I use 3D printing? How can I go from CAD to 3D printing in just 15 minutes? A quick overview of the 3D printing process. Adapting my existing designs for 3D printing, and a quick case study of how we can quickly iterate a tooling design and go to 3D printing. So why use 3D printing? Right? It's because we're waiting weeks and weeks for results. The ability that 3D printing gives you is to rapidly iterate your designs and your parts You can avoid the lengthy internal PO and RFQ process. And you can mature your engineering work faster. So what does that mean? This is the kind of cost of machining tooling, right? You go from CAD to developing a drawing or a blueprint. There's some backlog, whether you shop this out, whether you have to go through your purchasing team and they have to get RFQs out to get quotes. And then you finally submit the PO, then the machining happens, and finally you get the part in your hand. Now, if you did this internally, that might run through the same process, right? You CAD in your part in SOLIDWORKS, you get your drawing done in SOLIDWORKS, you establish that revision, you put that drawing in front of a machinist or a programmer that now needs to program the machine. Now the machinist is actually doing the machining and finally you get your part. For one-off tooling, for low-volume parts, this becomes very, one, not cost-effective, and two, time-consuming. So in that time it takes you to get one design iteration. If we removed drawing, backlog, and delivery with 3D printing, you can go from the CAD that's in your SOLIDWORKS to 3D printing that part, drastically shortening that design cycle. So in the same time it took you to do one design iteration by machining, you can do 3 design iterations with 3D printing. When you're 3D printing, there is a quantity where you will break even. With machining, the more you machine, the cheaper the cost is per part. With additive manufacturing, you kind of have the cost of the part is consistent no matter how many parts you produce. Let's say you print one part, printing 100 parts is still going to cost the same per part. So this is where your break-even point is. So everywhere left of that break-even point is where additive manufacturing with 3D printing is going to be beneficial to you and your business. At high production volumes, with one printer, it's not going to get you to that production volume. Multiple printers for low volume production is where we see this fitting, as well as 1 or 2 very low cost parts or low volume parts so that you get that cost per part low. So how do we go from CAD to 3D printing in 15 minutes? So this is the typical 3D printing workflow. Right, we go from CAD and SOLIDWORKS to slicing in our Eiger software to 3D printing on our 3D printers. And it's very simple. We'll take this part, for example. This is an end effector or a gripper for one of our customers, Dixon Valves. It carries this very heavy steel valve. Taking that gripper, you have a standard gripper that's in CAD, right? You pull this part up in SOLIDWORKS, your generic blank gripper. Imagine if you had a blank tooling or a set of hard jaws. You pull it up in SOLIDWORKS. You take that workpiece that you want to grip or conform your tooling around. Make that workpiece interfere with your tooling or your work holding, and do a Boolean subtract to remove that material away from your tooling. Now you have that conformal geometry for that end, that workpiece that you want to conform your tooling around. Clean up some of the edges. In this case, we added kind of 2 cavities, 2 little cutouts there for key inserts, just off-the-shelf inserts to serve as wear surfaces. Now you have a set of grippers that are conformal to that workpiece. Import that conformal tooling now into our Eiger software. On the top right, you're able to select your materials. Currently we have, for our composite materials, we have onyx, We have nylon white. We also have our new released material Onyx FR, which is a fire retardant onyx. In the reinforcement materials, we have the option of further reinforcing your parts, which we'll dive deeper into in a minute. And once you have those materials picked out, all you do is click print on the bottom right, and you're printing your tooling. So just take a step back in 3D printing processes. There are many, many, many options out there. If you look across the board, there are probably over 15 different options for 3D printers. So how do I know which one to go with? We're going to talk specifically today about FDM, or fused deposition modeling printing, which is probably what you're more aware of. Stratasys, or some of the big names, MakerBot, if you've heard of them before. Markforged is also in this category. And how FDM, or the fused filament fabrication 3D printing works is it melts a feedstock and extrudes it out of the nozzle one layer at a time. So how I like to describe it is imagine a high precision hot glue gun that is extruding material one layer by layer. So again, that workflow, you go from CAD and SolidWorks to slicing your CADed part in our slicing software, and then you 3D print it. So you may be asking, what is slicing? What slicing is essentially taking that part and dividing that part layer by layer so that the machine understands how to print it, right? So you take your part, you choose the part orientation, you pick the materials, you pick the density fills, and then it will divide it into many, many layers so that the printer understands how to print it. If you guys are familiar with CAM, for CNC machining, it's the same idea, right? Slicing takes in the part information and generates a G-code, a toolpath, so that the print head can actually, or the high precision glue gun can actually move around and produce your part. And that's how it's defining that same part here with slicing. So if we take that same gripper jaw, that work holding piece that we designed earlier, we import it into Eiger for slicing, what it's going to do is divide each one of those into layers that the printer can actually print. So here you kind of see how it's going to, at a high level, print that part. In continuous filament fabrication, this is where Markforged really separates itself from the competition, from your Stratasys, from your MakerBots, because we were all looped into that same FDM, high precision hot glue gun 3D printing. Where Markforged steps above the competition is with what we call CFF, continuous filament fabrication. And what that is you take your part in CAD, once again, you slice it, but now you also reinforce it, and then you print. So what is reinforcing? Again, these gripper jaws, right? For Dixon valves, it picks up that very, very heavy steel valve. Now, when you think about that, if you're printing in just plastic, is that plastic strong enough? Most likely no. When you take your part and break it down to how Markforged is going to print it, we'll take a cross-sectional view and look at it from the top. We're actually reinforcing this part with what we call continuous fiber routing all around the perimeter of that gripper. So what you're seeing here is that part will print in plastic, but it will also reinforce it with a second nozzle. There's a second high precision hot glue gun on our print head that will lay down continuous fiber. Now that continuous fiber can be carbon fiber, it can be Kevlar, it can be fiberglass, or high strength, high temp fiberglass. And all that continuous fiber, what it does, it forms what you can imagine as a continuous rope or a fence on the perimeter of this part. So that when this part is stressed, when it is put in tension, compression, it's not only the plastic that's absorbing that stress, it's that continuous fiber, that carbon fiber, the Kevlar, the fiberglass. It's actually resisting that load. And this is what it actually looks like in an actual 3D printed part, a cross-section of an actual 3D printed part. And this is, in this example, this is Kevlar that's been laid in here. And that's what it looked like inside one of our printers. Now you can see on the bottom right here, where you see the two plastic tubes feeding into, that's the print head. So it's one print head with two high precision hot glue guns on there. So as one extrudes the black material or the plastic material, the other is extruding the continuous fiber material that reinforces your part. Now we talked about composite printing, so let me talk a little bit about our metal printing and how we became the #1 metal 3D printing company in the world. And we've launched our metal printing back last February 2018. So only in a year we've dominated the market. It's because our method of printing is called atomic diffusion additive manufacturing, or in other words, ADAM. Now, how is ADAM different for metal printing than any metal printing that's out on the market? One, ADAM is a safer alternative to the metal printing you're used to today. The metal printing that you're probably familiar with or seen in the past is DMLS, direct metal laser sintering, which means there is free-flowing metal powder that's being sintered and welded. This process has no free-flowing metal powder. That means there's nothing that you can breathe in that will hurt you, there's nothing that will get on your skin that will hurt you, and there's nothing that's highly combustible. When you're dealing with fine metal powders, you have three major safety concerns to be aware of. With ADAM, those concerns are removed because our process of printing is the same as our process for composites. We spool up the metal powder in a binder material into a filament, right? So once again, we have a high precision hot glue gun extruding a wax plus polymer plus metal powder mix to form the shape of your part. So the step for ADAM is you design your CAD, you print again in the FDM style, high precision hot glue gun. It has the metal powder mixed in with the wax and the plastic. Then you wash your part in the provided wash, and then you sinter your part in the provided sinter oven. And finally, you get your part. So how does that process work? Essentially, once again, your metal powder is bounded by a wax and a polymer, right? So there's no free-flowing metal powder throughout any part of this printing process. Once that part is printed, you debind it in the wash, so it removes the wax. Now you take that part out of the wash, you put it into our sinter oven, and that will remove the rest of the polymers. When sintering begins, there are pores created by the wax loss and the polymer loss, and the metal particles will begin to diffuse together. Right? This connection, this is where all the IP lies. Is when I'm doing 17.4 stainless steel, how does this interaction occur? When I'm doing H13 tool steel, what temperature and how does this interaction occur? When I'm looking at A2 tool steel, 316L stainless, D2 tool steel, titanium 6.4, how do all these parts interact at the molecular level during sintering? And after sinter, that's when you get your final part. So what's great about our Eiger software, one, we have really brilliant software engineers that have developed the technology so that you do not have to worry about that shrinkage, right? You may be asking, well, Sean, I have my part designed this way, but you're telling me that there's wax and polymers added when I'm printing. That means the part's going to be bigger. That's correct. It's going to be 20% bigger, and during sintering, it's actually going to shrink back down the size. How that works is our software engineers have designed in the scaling so that you design your part in SOLIDWORKS to what you want, to what you need at nominal. You import that STL into our Eiger software, and our Eiger software will automatically scale it up so that when it does shrink in sintering, it comes out as designed. So how does it do this? In our Eiger interface, you can see on the top left, that's always where your information about your parts can be located. So all your part details, your printed dimensions, you can see are 20% larger in the XYZ than your final dimensions. That's the scaling that's already occurred within our slicing software. Remember, the slicing software is what generates that G-code, that communication to the printer as to how to print that part. You're also going to get the print time, the minimum wash time to debind your part, so to remove all that wax, and the sinter time is about a day, about 24 hours. Depending on what material you choose, you're going to get your material cost, the mass of the part, and then the amount of volume of metal is actually being used is what's generating the cost of your part. Now on the bottom left, you can see it will notify you that the part has been scaled up to account for that shrinkage. So we can kind of take a quick look at how that metal printing process works. All right, here's a time lapse of the metal printing. As you can see, the build plate drops down, and the high precision hot glue gun that's on top is extruding the part layer by layer, creating that same bracket that we saw. Once that print is done, now this is the other fantastic thing about the atom printing process and what has moved Markforged to be the #1 3D metal printing company in the world is that removing your part after print is very easy. In DMLS, you actually have a build plate that you are welding onto, essentially, and at the end of the print, powder printing, you have to have a wire EDM to cut that part off and then grind your build plate back to flat. With Markforged's 3D printing, all you do is, once the printing is done, you open up the print chamber, you pull your part off the build plate, and it's as easy as picking that part and peeling it away from that print sheet. And now what you see there is that bracket. That is the green state part. That bracket is 20% larger in XYZ than the as designed dimensions. It's 17/4 stainless steel, bounded by wax and polymer. From there, we will drop that part into the wash. And this is kind of a quick overview of what the wash process looks like. You have what is a wire basket and a solvent that's boiling in the wash itself. It's called Opteon Scion or Opteon SF79. It's an industrial degreaser. It has been approved by the Southern California Air Emissions for use in the state of California. We do have a ventilation unit on the opposite side where it provides active drying and ventilation of the unit. Because this does evaporate at a lower temperature, we do keep it sealed, as you can see from the doors. Now, the engineer here is placing that printed part into the wire basket and dropping it into the solvent itself. As you can see, into the wash, there's actually condensing coils, so it is a self-contained unit. As the vapor wants to escape, the condensing units are actually capturing it and dropping it back into the wash. So part drying, we won't have to sit through that. It just sets it on the other side. Now this is loading our sintering. So remember the 3 steps. Prints, it washes by debinding, and then it sinters. This is where the eyepiece sits. How hot do I keep it? How long do I hold it at that temperature? How is the molecular forces going to interact with each other? And how are we relieving internal stresses? So here, we'll watch as the engineer takes the part, places it on what we call the setter plate. The setter plate then is placed into the sinter oven. The sinter oven is shut and sealed, and 24 hours later, you will have your fully sintered metal part. And all this is being tracked on our Eiger software, our slicing software. Everything, whether you're doing composite printing or metal printing, it's all on the exact same software. So after you take the part out of the sinter, you'll have a fully sintered 17-4 stainless steel part. And with your finished part, you can see that we actually print on what we call a raft. So what that raft does is it helps with the drag forces and uniform shrinkage during sintering. If you place a part onto the setter plate, and as it shrinks, if you have very thin regions, that part may shrink and be differently than a region that has more material. And as it drags along the setter plate, you may have deformation of your part, or your part may break during sintering. So how we resolve this is printing on a raft that will allow for uniform shrinking. So how do I adapt my existing designs for 3D printing? There's a couple of features that we can consider and that we will talk about today. Threaded features, cantilevers and overhangs, as well as surface finish. So threaded features, there's a couple of options here. I definitely suggest the options on our left. The heat set inserts, the square nuts, and the hex nuts are going to get you the best pull out strength because you are getting that metal to metal contact. That bolt, when you have helical inserts or when you have tapped or printed threads, they could strip easily, whereas a heat set insert, square nut, or a hex nut is going to give you the best pull-out strength. These can be purchased off of McMaster-Carr or off the shelf, very easy to install. Threaded inserts with heat set inserts easily melt into the part with a soldering iron. This is going to be most likely your strongest threads, especially if you reinforce your part so that when these are being pulled and trying to strip out, that it hits a wall of continuous fiber that's resisting that thread from escaping out of your part. You can also use captive nuts, right? So what we've done with this tube bending die is we've actually created a undercut so that the hex nuts can drop into location, and from the opposite side, the bolt draws it. You can also embed components. So mid-print, you can pull your build plate out of the printer, drop in your hex nuts, place it back onto the printer, and it will print right over those hex nuts, therefore capturing and embedding those hex nuts as threads into your part. And what you see here is we have the ability, or it's designed in so that when you remove the build plate to when you place the build plate back on, it can go back to within 1 micron of where it was. So you're not losing out on dimensional accuracy. Threaded features with helical inserts. they are good, but you don't get as much increase in pull-out strength. These are great when you have limited real estate. If you don't have the real estate to put in a hex nut or a square nut or even a heat set insert, which is preferred, but you can use helical inserts instead of printing or tapping your threads. So things you want to take away here: avoid printing your threads whenever possible, right? Pull-out strength is probably only as good as that nylon. No matter how much continuous fiber you put around it, it's not going to be enough to hold that thread in. Printing thread sizes larger than M3 and 8 are best, and it's best printed in the Z direction, so perpendicular to the build plate. And it's only good for a single installation. If you're constantly putting threads in and out, that's where you're going to see additional wear over time. And this is just a quick slide to show when you should go with what. So you can see heat set inserts are great in pull-out strength, torque out strength, for small profiles, and ease of installation. At the very end, you're printed. If you have to go with it, it's due to your small profile, right? Limited real estate. Markforged support material. So if you're printing this door handle, you're going to see that material in the center there. That's all what we call support material. So similar to these overhangs or bridges, it's going to place in. The slicing software is going to see that that is an overhang. It's going to place in what we call our support material. And it's the same material as the material you're printing with. So if you're printing with onyx, it's going to print with onyx. You're printing with stainless steel 17.4, it's going to print with stainless steel 17.4. If it's H13 tool steel, it's going to print with H13 tool steel. But what it's going to do is it has to print something to support that sealing. When you have gravity working against you, you have to have something to hold it up. And during sintering, something to hold that up is going to help for uniform shrinking during the sintering process. What we recommend here is chamfering those supports so that they are therefore self-supporting. Self-supporting structures are best. You're going to have better dimensional accuracy. You're going to have better surface finish. Another way to avoid having overhangs is 45 degrees. Less than 45 degrees, you're not going to have overhang, or you're not going to need supports. If you're more than 45 degrees, then you're going to need supports. You can also do self-supporting holes. So instead of a hole, create a teardrop hole or a diamond hole. Now these are unconventional for machining because why would you have an odd-shaped hole? But for 3D printing, for the hole at the top of the hole, whenever you have a horizontal one, it's going to want to place support material to support the very top of that hole. If you use a teardrop or a diamond, you eliminate that possibility. Similar to here, this is an end of arm tooling, a vacuum end of arm tooling, and within the inside, they've created diamond channels that route that vacuum. No support was necessary to print that part. And the final thing we'll talk about is surface finish, right? The big takeaway here is if you want great surface finish, the trade-off is print time. If you want fast print times, your trade-off is surface finish. At 50 microns or 2 thou, your print time is probably going to be 4 times as much as if you were printing in 200 microns or 8 thou. And that surface finish, depending on the application, can be very critical or it may not matter. For our industrial units, the highest resolution is 50 microns. It gives you a very, very fine surface finish, and you can dial it up to 200 microns to optimize for print speed. So remember, when choosing a layer height, thicker prints faster. Thinner will give you a much better surface finish, but will print slower. The default is around 100 microns for our Mark II, And our industrial units are at 100 microns as well, but you can go to the 50 microns. So we'll take a quick look at a design example. This is showing how we can go from iterating in CAD to 3D printing. Right. For example, this is again a end effector that is grabbing now the inside of a valve, and this valve has threads on the ID. It's a design of 3-jaw gripper, and it's seeing a lot of wear due to the threads in the ID of that workpiece it's lifting. The 1-month PM schedule is much too short, so the challenge is how do we extend the jaw life to extend the jaw life here so that we can reduce the PM schedule or increase the PM schedule. So you can see here that ID, internal threads on the ID, is what's eating at the 3 jaws that have been printed. So the solution is to fit a steel dowel pin at that contact surface. So again, similar to how we added the key inserts, here we're adding in off-the-shelf dowel pins. 3D printing makes that design very easy to do, right? Pull in the SolidWorks, drop in 2 holes for press fit dowel pins, order your dowel pins, press them in, you're ready to go. But what if the jaw pressures cause the pins to damage the ID threads? So now your work holding is actually damaging your workpiece. 3D printing offers a high geometric control and fast iteration cycles. So what that means is, this is that jaw design, your first iteration. All right, you're adding in to each jaw 2 points of contact. 15 minutes later, you added an additional set of point of contact. So now you have 4 points of contact per jaw. Now, does that relieve enough of the stress and the wear on your threads? Maybe not. Maybe you go another 15 minutes and you add in now 6 points of contact per jaw. With rapid design iterations, you can evaluate your baseline design, iteration 1, Rev 1, to Rev 2 to Rev 3, reducing the point contact force, allowing you to print all 3 of these designs in one go and have all of these designs printed and ready to test tomorrow rather than next week or 2 weeks, or if you're shopping it out, typically 4 weeks. So a little bit about Markforged. We're trusted by industry leaders, right? What made us the #1 metal 3D printing company in the world is not because we're not trusted by industry leaders. We're building partnerships across different industries, and with these partnerships, we're exploring new avenues as to what metals to introduce, what materials to introduce. As I noted on earlier in the presentation, we released Onyx Fire Retardant, or FR, very recently. It's very applicable to the aerospace companies, to the auto manufacturing companies. Anyone that needs fire-resistant or fire-retardant materials, we're opening up that avenue. Down the road, we're looking at releasing on the metal side more tool steels. We have A2 that's launching. We have H13 that already exists. We're looking forward to D2 tool steel as well. We're also going into titanium 6.4, which is going to be applicable to the healthcare industries, to the aerospace industry. Inco 625, also to aerospace, to oil and gas. So we're definitely working closely with these industry leaders to drive our vision, our product for the next coming years. So a little bit about Markforged. We're founded out of MIT back in 2013. In 2014 is when we launched our first composite printer. We're headquartered up in Boston, Massachusetts. We have 200 plus employees. And we control the entire ecosystem for 3D printing. What that means is We have software engineers that develop the software, the Eiger slicing software. We have contract manufacturers local in Boston that are manufacturing our printers. And we are actually, as I hinted on earlier in the presentation, expanding into a new manufacturing center where we're producing in-house engineering-grade materials. By controlling all three of these variables is the only way to guarantee that you have the quality parts coming off our printer, the repeatability, as well as the reliability. See, Markforged enables our customers to produce a strong, functional part faster and at a lower cost that serve the needs of a wide range of applications across the entire manufacturing lifecycle. Thank you guys. I appreciate your time. So first question is, are the printers portable? They seem pretty small, not the metal oven, right? So by portable, if you mean, are we able to transfer them? Are we able to move them? Yes, they are the Metal X printer. We move around to trade shows all the time. Do I recommend moving it around? No. If you needed to move it from office to office, it's fine. If you need to have it in the back of your car to move it, it's also fine. But on a regular basis, it's usually best if that printer had a central location that, and once it's set up, you kind of just leave it and let it go. The more you move it around and introduce possible scenarios where it could get damaged, it could result in failures, especially the smaller printers that do not have the automated bed leveling. As you can imagine, a proper print comes from setting up a proper datum, right? So imagine CNC machining. Without establishing your primary datum, the rest of your part is going to be garbage. And that's the same way with 3D printing. That build plate is your primary datum. Being able to have it consistent across builds is important. And when you move the printer around too much, it could disrupt that primary datum. Our industrial series printers can handle that a lot better because it does automate that process. It takes a laser that will actually scan the bed for 32 points and bed level for you. And also our metal printer does the same way. It touches with a pressure transducer on its print head that will level your bed or find the level bed for you and establish that primary datum. The metal printer is definitely not movable. You do not want to move that metal printer out or the metal oven after it's been installed. How would you compare Markforged larger printers to Stratasys F370? So that's a good question. I actually had a breakdown earlier, but I can just talk to it. Stratasys is great for your rapid prototyping, right? If you want to do fit form checks, they're great. But at the end of the day, it's still a plastic material. You're still printing with an ABS or it's still a polymer. Whereas Markforged, and that's what we're saying separates ourselves from the rest of that market, that competition, is we can print with continuous fiber. Now, if you've ever messed around with Kevlar or carbon fiber, you understand how strong that fiber actually is. When we're reinforcing our parts with continuous fiber, we're approaching the strengths and exceeding it in some applications, 6061 aluminum. That's how we're able to actually use, customers are actually able to use our 3D printed parts that are reinforced with this continuous fiber for milling operations, for welding applications, welding fixtures, soft jaws. This is where we see the technology being highly applicable. It's functional as well as fit form checks. If you're only looking for fit form, then Stratasys is going to be the way to go. If you need something that's going to be functional as well, then you're going to want a Markforged printer. Third question is, how did you make sure the expanding and shrinking process is accurate? What tolerances can you hold? So it's a very good question. In metal printing, I'm assuming that's what you're referring to, the shrinking process is dialed in by our metallurgists as well as our software engineers. We're holding plus or minus 125, which is about plus or minus 5 thou in tolerances. And so there will be geometries that may be outside of that, and there may be geometries that we hit dead on. But with a year since launch, we are, big data is a big thing nowadays, right? We're collecting all this data from prints. So everything, like I said, is tied to Eiger. We're collecting information as to how it's printing, collecting feedback from our customers, and constantly iterating and updating our software as well as our hardware so that we can maintain these tolerances and stay within spec. Looking into the future, our goal is to better utilize that laser printer or the laser micrometer that's on our industrial series for our composites. We're going to be able to start scanning your parts and getting a better visual of where, like almost like heat map, like geomagic, where we're outside of spec and where we're in spec, and adapt to that on the next print. The fourth question is, what if we need a part with moving parts? What's the clearance to have parts movable? If you're talking about printing like a living hinge or a door hinge, your gaps, you just have to create enough for clearance. We're printing about 0.4 millimeters in walls. So I had a customer the other day that designed a part where there was enough clearance and there was support material in there to keep imagine a door hinge with a pin. And they were able to start moving that door hinge and just snapping away the support material, and it ended up falling out. Let's see, next question, what post-processing can you do on the nylon? Can you color it? It's a good question. We've had customers that have actually colored it, primed it, and then painted it, spray painted it. We've had customers that have done electroless nickel plating and then chromed it afterwards. The nylon white material that we have, we're actually looking at going into different colors and producing different colors. Definitely send us some recommendations on colors that you would like to see in the applications and why you want those colors. We're definitely trying to build, like I was saying, we listen to our customers a lot. That's how we got to where we are. We like to get a better understanding of what direction product needs to go. So any kind of recommendations on colors and why will really help. Last question here, what can we use if we are not allowed to use the cloud? Military group. Great question. So one of our strongest customers is the U.S. Navy. And we have solutions for our DoD customers that is completely offline. So our Eiger software, yes, it is cloud, but we also have a local storage that doesn't send any part files to the cloud. And then our final option that's designed for our DoD customers is called on-premise. That software option is completely removed from the internet. It does not require internet to operate. You take your parts, you slice it on your computer, it generates the G code for you to print, and that's it. Every time you want to print that part though, you have to generate that G code. But we're looking product vision down the line for the U.S. Navy, for our DoD customers, for those government contractor customers. Like I say, I used to work for Pratt & Whitney, so I completely understand when you cannot be on the cloud. You cannot be connected to the internet, but there's still the luxury of the seamless pull your parts into the computer, have it printed. That's the vision, is creating an entire ecosystem, or not new software, but a better user interface for that. But we do have software today that allows our military customers to be able to print. And that's all the questions I received from Chris. Are there any more?
Can you print from Cura directly, or do you have to use Eiger?
Yes, so you do have to use our Eiger software. Like I was saying, with the ecosystem we built, it's the software, the hardware, as well as the materials. We can't ensure part quality and reliability and repeatability without utilizing all three of those. If we change one of the variables, we're introducing a source of error, right? Using Cura to slice your parts, it's not designed, or it's not producing the G code specific to our printers, whereas using Eiger is producing that G code specific to our printers to communicate exactly how it needs to print. And Eiger allows you to reinforce your parts with the continuous fiber. There's no other technology out there that's allowing you to do that. On our composite side, that is where our IP is.
All right. Looks like that's all the questions. We're coming up on an hour, so I appreciate everybody's attendance. LaShawn, again, fantastic job. Really enjoyed your presentation. So having said that, I just want to thank everybody who joined us, and hope you have a nice day. Thank you. Bye-bye.